Hey guys, welcome back to Bottom Up Chem. We're looking at the new course and we're going to look at the particular nature of matter, and I'm going to change format a little bit here and kind of going to do a watch along. These are some notes I was making while I was in class. And so firstly, we're going to look at defining elements, compounds and mixtures. Elements being atoms with the same number of protons, and compounds with multiple elements chemically bonded. So both of these can form molecules. So any atoms that are bonded together can be considered a molecule. So we could have the same type of atom bonded together. We could have different atoms bonded together. So for example, the nitrogen element is a molecule, 2 nitrogen atoms, and CO2 is a molecule, but that is a compound. So kind of differentiating between element and compound, and we can have molecules of both. A molecule just means any chemically bonded structure. So we can think about air, really. So the air around us, we have things like oxygen, carbon dioxide, nitrogen, argon, got loads of other trace things. All of these gases are in the air around us all of the time. Okay, they have different internal chemical bonds. So you can see they have double, single bonds. However, they are not chemically bound to each other. There is a only weak attraction between them. And so this is a classic example of a mixture. A mixture is just any combination of substances really that are not chemically bound. Now, that doesn't mean they have no interactions, and we'll cover that later in the course, but it does mean that they're not chemically bonded. We don't have that electron sharing characterizing our normal bonds. Okay, in good old-fashioned style, we're going to have a little progress check. So get your whiteboards out, get ready for a question. First question then, which of these counts as a mixture? A drinks can, an LDPE plastic bag, a regular plastic bag, a bag containing sand, sugar and salt, or a silver necklace. Pause the video to have a go at that. Pop them up. Okay, hopefully you got that is a bag containing sand, sugar and salt. And the reason for that being is that a drinks can is made of aluminium, plastic bag is just the plastic molecule extended, and a silver necklace being just pure silver. Now, obviously in real life, I'm aware that these are alloys, and we can discuss the slight difference between alloys and mixtures later when we look at bonding. But really, when we look at mixtures, we're looking at those non-chemically bound, which is why our alloys don't really count as mixtures in the way we're looking at them for this video. Okay, so then we can start thinking about solids, liquids and gases, probably something you've covered before, but just to cover this off, solids are tightly packed chemical structures. Okay, they have strong chemical bonds between each of the molecules, and they form these kind of regular repeating structures. They don't really change shape unless there is, some kind of force, external force applied. Yes, not gravity, those kind of things, but they tend to maintain their shape. They're not compressible. So when I say compressible, that means we can't squish them down. So a common misconception is with liquids that they also have much more space between them. However, these are also very tightly packed. So liquids tend to be very incompressible as well, but instead of the particles being fit in a rigid lattice structure, they instead have a free movement over each other. However, the molecules are often very similarly spaced to a solid. So we have not as strong bonds between the molecules. However, the actual freedom of movement is increased because of that, but it doesn't mean there is a really large space. So when we think about gases, that's where we really move into the territory of lots of space between the molecules, and those we could describe as having, relatively little, zero, even if you like. We'll come to that when we do ideal gases. Attraction between them, and that means they're very compressible because there's so much space we can push them towards each other, and it means they fill a space. Okay, you fart in one corner of the room and everyone on the other side of the room can smell the fart. Okay. Okay, we can label these states of matter as gas with a little g. We can label them as S for solid. We can label them as L for liquid. But we'll also commonly see this symbol AQ. Okay, that stands for aqueous, dissolved in water. And really, that representation can be used a lot. We can use that for dissolving in alcohol, which we would see ALC. If we heat these things up to crazy high temperatures and pressures, we can end up with plasma, which is another state of matter that we don't really cover in the IB. It's very, very high energy. It's just basically a soup of protons and electrons. So hopefully that should be somewhat familiar if you've studied a little bit of science before. Now we want to kind of link that to what does it mean to change between each of these states? What does it mean to change from a solid to a liquid to a gas and vice versa? So let's model our state changes by kind of graphing energy, right? When we think about heating something up, we are adding energy to the system. And as we add energy, we expect the temperature rise. Right? That's kind of normal. So we can graph that. We have heat and we have temperature on the y-axis. So you'll see the shape that I've got here is representative of many normal substances that will go through a solid, liquid, and gas phase. These plateaus represent phase changes. We have 1 and then we have 2. The initial plateau represents our transition from a solid into a liquid, and the second one represents the liquid into a gas. The reason we can model it this way is we can think about as we increase the heat, we are increasing the amount of energy in the system. So why then do we increase, solid, it increases in temperature, it gets hotter, hotter. Think about a pan on a hob. It gets hotter, hotter, and hotter until a certain point where actually the temperature doesn't change, but we can still add energy. Well, if we think back to our diagrams of these, what we're doing is at that point, which is obviously the melting point, we can name these solid to liquid is melting. At that point, we are overcoming the forces holding those different molecules together. And so all of that energy we're adding is going into that process, which overcomes that and causes the solid to become a liquid, aka melting. Now, if we have a liquid and we keep adding energy, then just like heating up a pan of hot water, we keep getting that temperature rising and rising and rising until a certain point where we see again this plateau. As we add more and more and more energy, we don't see any temperature change. Well, what's happening? Well, now thinking back to our liquid, very close together, still some energy holding those particles together, some intermolecular forces. Well, that energy goes towards breaking those even further, and we go into our gas phase. That obviously being called evaporation. Now, just as we can go up through those, we can also go down through those phases as well. So we have the transition going from a gas to a liquid, and we also have the transition going from a liquid to a solid. So gas going to a liquid is condensation, and going from a liquid to a solid is freezing. And that's all fine and dandy for things like water. However, when we think about things like CO2, it's not quite that simple. So if we take a very similar graph, but instead of having these two transitions going from a solid to a liquid and then a liquid to a gas, indeed, some substances such as CO2 will go straight from a solid to the gas phase. Okay, and this is called sublimation. Indeed, if you're a theatre fan and you have all that spooky smoking around the feet of the actors in scenes where there's meant to be an atmosphere, that is actually the use of so-called dry ice or solid CO2. If you take solid CO2 and you throw it onto some water, it very quickly evaporates, and it's quite a dense gas, and then that spreads around as the fog, and that is what we call dry ice. creating that atmosphere. So the transition for that from solid to gas is called sublimation. Okay, so that is going from a solid to a gas, the sublime, you could say. Now, going back down the other way, okay, so that's we are removing energy and we're going from the gas phase back down to the solid phase. We call that deposition. Why, when a small amount of energy is added to water at 378 Kelvin, does the temperature of the sample not change? Pause the video to have a little think about that. Pop them up. Okay, great. If you got that was because at 378, maybe a bit of misdirection by using Kelvin here, at 378, 100 degrees, the water is no longer increasing in temperature because the energy is being used to overcome the bonds between the water molecules. Then fantastic. So you saw in that question there that I mentioned Kelvin. So what's a Kelvin? Why is it around? And why don't we just use degrees? Well, thinking about this graph again, the good thing is a Kelvin and a degree are effectively the same increment. Okay, so on the right over here, the difference between 6 and 7 degrees is 1 degree. It's also 1 Kelvin. Okay, so why do we use this? Well, Kelvin is the standard SI unit for temperature. Okay, it's the equivalent for temperature that the meter is for a distance. And what that allows us, it allows us an absolute zero. Okay, so absolute zero is not 0 in degrees centigrade. In fact, 0 in degrees centigrade is 273.13 something, but at IB, we're just going to take it as 0 degrees centigrade is actually 273 Kelvin. Okay. Now, why is this significant? Well, at absolute zero, we've been talking about these phase changes. We've been talking about things moving around, solids vibrating, and the molecules of liquid sliding over each other and gases bouncing around, and that kind of Brownian motion. Those things would not happen at absolute zero. Absolute zero is a theoretical point at which all movement stops. Okay? And what this kind of, the significance of this statement and the significance of absolute zero allows us this equivocation between temperature and energy. Okay, if absolute zero means that there's no movement, then temperature is directly related to movement, which is fundamentally true. Temperature is kind of a measure of the vibration of things around us, the vibration of particles. Indeed, we define this. Temperature is the average energy of the particles. And no, we're not going to be looking at how to calculate what that would be or if that's interesting, but how, when we do look at our kinetics, we will look at how that links to the process of chemical reactions in a little bit more detail. But that's kind of, an introduction to our Kelvin and why Kelvin is so important. So, lastly then, let's have a look at some simple techniques. Okay, what do I mean by techniques? Well, I want to talk about separating mixtures. Okay, so the most simple example I could think of here, right, is take a cup of water. You leave a cup of water on a windowsill, and over time, there's less water in the cup. What's happening? Well, you might go, well, obviously, sir, it's evaporating. Yep, okay, it is. And indeed, what is evaporating is pure water, just H2O just going out into the atmosphere. Okay, so whatever you had in the glass at the beginning, if it was pure water, then you're going to end up just slowly dissolving that water. However, what's likely to be the case, especially if it's just a cup of water, is you're going to have dissolved substances, unless it's distilled water, in that water. And so as you slowly evaporate all of that water off, those dissolved substances and salts will slowly begin to deposit on the bottom of the cup, especially as you run out of solvent. Okay, the solvent in this case being water. They are left as a residue kind of on the side of the cup. So this is kind of a really simple example of separation, right? By accident, we accidentally separated the water from whatever residue was in the whatever solids were in the water, which we may or may not have wanted to do. However, we may want to do this, right? And so there are a couple of different ways that we may want to go about doing this. One example of this is kind of taking this same concept to the extreme is distillation. Okay, so in distillation, we're actually going to pretty much use the same process, right? So we've got a round bottom flask, okay, and that round bottom flask has whatever liquid in it. Let's take the same water as we had before, and that is connected via this T joint to a Liebig condenser. Okay, that is this thing going along the right-hand side here. So the Liebig condenser is this double-walled piece of glassware where around the outside we force water up from the bottom, and then water comes out the top. And what that does is that removes any excess energy from this chamber. So as we add heat, okay, so we evaporate it. As we add heat and then remove the heat from that gaseous phase, we end up recondensing that solvent. And that when we can collect that pure solvent. So if we wanted to collect that water that you had with all of those salts in the beginning, we could go through a process of distillation and we would get our pure solvent at the end, condensing it back into a liquid. And what would be left on the bottom of the round bottom flask, again, is the same residue. Okay, so this is a much more controlled approach. Now, we might not want to necessarily, we might not be looking for the residue. We might also want the solvent. We don't have to do this. I'm just using the example of water here. This is just a technique. Okay, indeed, if we, it's not a method of separation, but if we were to put the Liebig condenser directly into the round bottom flask, that would be refluxing, which is a method of, more of a method of allowing a reaction to occur, which we'll look at later on in the course, not so much for right now. So yeah, that's kind of like, we're taking something simple that you may have heard of, and then we're kind of like, putting it on steroids. We're really beefing it up and making it more analytical in the way we can approach it. So we can think about the same about filtration, right? So you probably put like some filter paper in a funnel and poured some stuff through it. Okay, this is a very simple technique. The filter paper is a barrier for any undissolved solids. You pour the liquid with the dissolved solid through and you get some stuff come out the bottom. That's called the filtrate. And you get your precipitate that was left as a suspension, whatever was a solid in the top. That precipitate is left in the top and can be collected, whether it's salts or whatever solid was not dissolved in it. Okay, so this is a really, really simple technique. And again, we can improve this, and these techniques we'll use in a school lab. We can use a Buchner funnel, okay? And we do exactly the same technique. So in a Buchner funnel, instead what we do is we have a sidearm flask underneath in which the air is being dragged out. And what that does is that causes a suction on the filter on the top. And that allows all of that excess filtrate to be dragged through. Okay, if you've ever dissolved anything, if you've ever put anything through filter paper, it can be incredibly frustrating just waiting for it for ages and ages to slowly drip through. And obviously as the precipitate fills up the filter paper, that gets slower and slower. So it can be pretty annoying sometimes. So this Buchner funnel allows us to do this and really draw all the moisture through. Even in a position when we won't be wanting to collect this solid, we can begin washing that with solvent again, kind of cleaning that, and that might be something we're collecting, or we can be collecting the filtrate. It all depends. And so, these techniques, you're thinking, well, this is a lot. But just think about something stupid like coffee. I mean, it's not stupid if you're anything like me. It allows my day to function. So a normal cup of coffee, if you go around the world, coffee, or even your local coffee shop, can probably be made in many different ways, okay? In many parts of the Levant, you will find people making coffee in containers that look like this. They kind of have this conical shape, and what you'll find is the coffee is served and it has this slurry of coffee at the bottom, so that the water is steeping with the coffee together. Maybe it's stirred and then left, and then the coffee slowly settles at the bottom. And so it has this deliberate shape so that when you pour the coffee, not so much of the coffee solids are poured in with the coffee. Okay, so this is very simple technique. It's been used for very many centuries in many different cultures. And then we can think, okay, what about these kind of techniques? You go to the fancy cafe, or even if you've ever made with a little Mocha Master thing on your hob, where we're pushing steam through coffee. So how is that different? Well, we can think, we heat the coffee up, the liquid coffee, into gas, and then that gets forced through usually a little pressed format of coffee. Okay, this is a very common way. For the last 100 years, coffee has been made this way in both of these kind of techniques. And then that force, the gas condenses and again pulls out all of the dissolvable coffee from the coffee solids and is forced through a filter. Now, again, you can go even one step further with filtration. You can go to almost a basic filtration. You can use whether it's V60 or some kind of Chemex filter, but you use a regular coffee filter or even just an old drip coffee machine and just drip water through the coffee. It's kind of a slower potential method. However, this will get out even more solids. So what we can think of is coffee is this kind of thing that has both dissolved, it has solid suspension, but it also has dissolved compounds in it, okay? And the relative amount of these dissolved solids and these other things change the flavor profile, change everything about the coffee, okay? So, when people think about coffee, they think about caffeine, okay, this molecule here, which is like super soluble. So all of these types of coffee tend to get a lot of caffeine because most of the caffeine can be removed from coffee quite quickly because caffeine is quite soluble, depending on the grind. Maybe if you use a cafetiere, which if we really think about it, is kind of like a filtration method. Your grind, you might have to leave it a little while to get the caffeine, but in general, that's quite soluble. And so are a lot of the other acids that exist in coffees. Okay, so that's why coffee can be quite acidic. And these give, the coffee the light part of coffee. If it's, kind of an amber color, it's very bright coffee. These are all those dissolved acids and the caffeine. The darkness of coffee, this is very general. The darkness of coffee and the insoluble fibers and carbohydrates that are also present in coffee obviously come through in different amounts depending on the kind of method you use. So we could use the same coffee and use each of these techniques and get a very different tasting coffee because we would have more of that insoluble fiber because we can think about different ways we're filtering coffee is exactly the same as we might think about different ways to use filtration in a chemical setting. Another way we can separate things, which we don't tend to do with coffee, is through chromatography. So think about the time, you're in the shower, there's a puddle in the bottom of the shower, you're drying yourself, you're minding your own business, and you have accidentally left the corner of your towel in that little puddle of water. And before you know it, that water is halfway up the towel. Not great. Okay, so what's the problem here? Well, what's happened is the capillary action, of the solvent has meant that the solvent has moved up what we call, in this way, we call it a stationary phase. Okay, the stationary phase here is just the towel, the solid thing. So the solvent moves up, we call it a solvent front, moves up the stationary phase. So if we think about the towel, like if we're going to draw the towel here as a square, we can think about it, or as a rectangle even, we can think about it as the solvent front being how far the water travels up the towel. Now, different substances have different affinities for a solvent. Now, as I just said, some things in coffee, they really, really like to dissolve in water. Some things in coffee, not so much, okay? We call that an affinity for a solvent. So we can think here, if we take 2 parts of coffee, or even, to keep the towel metaphor, you can think of 2 hair dye, okay? And they were in the bottom, they were in the solution at the bottom, the water that was left in the bottom of the shower. And then after a while, we leave them and we find that they have moved a certain amount up the towel. So we can see that the red one has kind of not moved very far, and this kind of brown one has moved much further. So what does that kind of really mean? Well, it means that the red one doesn't have a lot of an affinity for the solvent, and the brown one has a higher affinity for the solvent, right? Because the brown one wants to dissolve in the water more, so moves a lot further with the water, okay? Whereas the red one has a lower affinity. Now, we call this the retention factor, okay? So retention just being like how much the solvent retains whatever it is we're trying to separate, in this case, whether it's dyes or coffee components. And there's a pretty simple way to calculate this, and we can call this RF, which is just the distance the substance moves divided by the distance of that solvent front. So for example, if we had a 10 centimeter solvent front and a 7 centimeter movement for this very small towel, isn't it? But anyway, then we would just simply do 7 over 10 or 0.7. However, if we took the red dye here and we just say that that is 1 centimeter, then that would be 1 over 10 or 0.1. Okay, these, it's dimensionless because we're dividing centimeters by centimeters and whatever unit you use, but it's just a relative factor, relative retention factor that allows us to determine the relative affinity for these things, for any substance really, to the solvent we're dissolving in, whether that be water or alcohol. Awesome. Thanks for joining me, and hope you like this format. Maybe a few more coming soon. As always, practice makes slightly better.